Hey guys, how's it going? Stoff here. What we're going to do is we're going to start on related rates. We'll talk more about derivatives later, but for right now, what we're going to do is we're going to dive in like I would have done in class. So we're just going to start with a problem, and as I work my way through this problem, I'm going to start to explain everything that's going on. So a spherical snowball is melting in such a way that its volume is decreasing at a rate of 1 centimeter cubed per minute. At what rate is the radius decreasing when the radius is 5 centimeters? So first off, I'd like to apologize for the overt capitalization and that little box that I couldn't figure out how to get rid of, but hopefully in the future I will get better at this. Now, what is a related rate? And to figure out what a related rate is, we first need to think about what's an equation. So we can see right here that I'm looking at a sphere and I'm talking about its volume. So we're going to start with the volume equation of a sphere where volume equals 4 over 3 pi r cubed. I'm assuming that all of you knew this because, well, I can't hear you yelling it at your screen right now. So I have volume equals 4 over 3 pi r cubed. What's this saying? And what it's saying is that my volume depends on my radius and my radius depends on my volume. Rather, and just going off on the side right here, if I had this sphere, check out my sweet drawing abilities, and we had a radius, say, of 2. Well, then my volume would be equal to 4 over 3 pi multiplied by 2 cubed. Or rather, it would be 4 over 3 pi multiplied by 8, which would give me 4 times 8, which is 32. So 32 pi over 3. Now, that's all good, but it gives me a very, very static interpretation of what's going on right here. When the radius is 2, my volume is 32 pi over 3. Let's say we want to change the size of this sphere. So I either want to increase it or decrease it. So taking my sphere, and what I'm going to do is with that awesome drawing that you guys have just seen, I'm either going to take it and I'm going to increase the size of it, or we're going to take it and we're going to decrease the size of it. Is there a way to get what we call a dynamic interpretation of this? And yes, there is. We accomplish this by using derivatives. So, in our question, the snowball is melting such a way that its volume is decreasing at a rate of 1 centimeter cubed per minute. If the volume is decreasing, that means that it's moving. We don't have a variable defined for this because I have my volume, which is my static volume, and my radius, which is my static radius, where the decreasing volume means it's going to be a dynamic value. If I wanted to say what that would be as a variable, it would be dv over dt. Because we remember the dv represents the change in the volume and the dt represents the change in the time. So if my volume is decreasing at a rate of 1 centimeter cubed per minute, that would mean that my volume is decreasing as a rate of time. Now, we're going to put this value as being negative 1 centimeter cubed per minute. Why am I putting it as a negative? Because the value is decreasing. Very, very importantly for related rates questions and as we go on, if the value is decreasing, we put a negative on it. If it's increasing, it's positive. Negative and positive have nothing to do with direction when we're talking about a related rates question. So going back to my original equation, I take the d over dt of this. Or rather, I want to see how this equation is going to change with time. So the d over dt of v would give me dv over dt. Equals, we notice that the only variable here is the r. Since the only variable is the r, 4 over 3 pi is just a coefficient. So my 3 comes down, leaving me 4 pi r squared. But we remember because of the chain rule, I have to have the dr over dt here. Now, what this gives me is this gives me a very, very dynamic interpretation of this. Or rather, this gives me a formula for a sphere that's always changing in size. It's increasing and it's decreasing. And if you could see my hands right now, my hands are moving back and forth, showing how much this is increasing or decreasing. Until I get my picture on this video, you'll just have to take my word for it. Next thing. I know that my radius is going to be 5 centimeters, and from before I know that my dV over dt, or the change in my volume over time, is -1 centimeters cubed per minute. So being very, very sloppy, I'm going to put these values in, not really paying heed to the units. We get -1 equals 4 pi, and then my radius is 5 squared dr over dt. Now this dr over dt, what would that change for? That would be the rate of change of the radius. So now using my awesome powers of mathematics, this gives me 100 pi dr over dt, or rather it gives me dr over dt equals -1 all over 100 pi. So that -1 over 100 pi would represent the rate of change of the radius as it regards to time. If we want the units on this, we're just going to go centimeters per minute. So, summing up what we've done. I had my snowball question and I know that my snowball is melting. The first thing that I did was I defined what the formula was. The formula for a sphere and volume is volume equals 4 over 3 pi r cubed. I then took the derivative of this with respect to time. Taking the derivative of it with respect to time gives me a very dynamic interpretation of the formula, and it basically says that as volume changes, it depends on my radius changing and on my radius. I substituted in the values, solved for the dr over dt, and then I found that the rate of change of the radius is -1 over 100 pi centimeters per minute. Thanks for listening, guys. Until the next one.